Welcome back to the deep dive, everybody. Today we're strapping in and getting ready for takeoff with a look at a topic that's absolutely crucial in aviation. You guessed it, aircraft weight and balance.
That's right.
Our learner this week sent in some really interesting material, primarily focusing on excerpts from the FAA's Weight and Balance Handbook. And get this, folks, there's a whole lot more to this than just making sure your luggage isn't over the limit. This is a real science.
Yeah, absolutely. It really is. What we're going to be diving into today are the fundamental principles, the core ideas behind how you actually determine the weight of an aircraft. And this is the critical part, how that weight is distributed.
Right.
And that all boils down to this process of figuring out what's called an aircraft's empty weight and the location of its center of gravity, or CG.
That's right, the CG. And, you know, this isn't just for pilots and mechanics out there, learner. Understanding weight and balance gives you a real solid understanding, a foundation in how aircraft operate safely and efficiently.
Yeah.
We're going way beyond just avoiding being overweight. We're talking about the incredible precision that goes into aviation.
Right.
And the best part, these concepts of load distribution and equilibrium, they're not just limited to airplanes. They pop up everywhere.
Everywhere.
In so many unexpected areas in our daily lives. It's fascinating. So our mission today is to really unpack this, to pull out the core ideas behind aircraft weighing and center of gravity determination, and explain why this is a non-negotiable part of aviation safety and performance.
Yeah.
Along the way, we'll demystify some of the terms and procedures involved. So let's get started. Why is getting this weight and balance right so vital? Why is it such a big deal?
Well, without a doubt, the number one reason is safety. Aircraft manufacturers, they don't just pull numbers out of thin air when it comes to loading limits.
Really?
They put aircraft through extensive flight testing to figure out the precise, safe operating envelope. I mean, think about it. An aircraft that's designed with a forward CG limit can become dangerously unstable in pitch if it's loaded too far aft,
Wow.
potentially leading to a stall that's unrecoverable, even for experienced pilots. This isn't just theoretical stuff. It's based on real-world simulations and flight tests that push the boundaries of safe operation.
So we're not just talking about whether a plane can physically take off. It's
Exactly.
much more nuanced than that.
Yeah. And while efficiency during flight is certainly a factor, a properly balanced aircraft will perform better. It'll use less fuel. Safety trumps everything.
Absolutely. Safety first.
Safety is paramount, no question about it. But what's important to understand here is it's not just about the total weight. The distribution of that weight, specifically where that CG is located, is equally, if not more important, for maintaining control of the aircraft.
So what are some of the dangers, the less obvious ones, of having improper weight distribution, even if you're within the weight limit?
Okay, so picture this. There are very specific forward and aft CG limits established for each aircraft.
Okay.
Now, if the CG falls outside of these limits, and this is where it gets tricky, it can seriously mess with the pilot's ability to control the aircraft.
Oh, wow.
Especially during critical phases of flight, like takeoff and landing. Imagine a CG that's too far forward. That can make it tough to raise the nose for takeoff, and you'll have a really nose-heavy feeling in flight, which means more force on the controls and potentially a really challenging landing. On the flip side, if the CG is too far aft, that can lead to instability, where the aircraft becomes super sensitive to control inputs, increasing the risk of a stall, especially at low speeds.
So it's a delicate balance, literally.
Yeah.
You need to find that sweet spot.
Exactly.
Now, who's ultimately responsible for ensuring all this weight and balance information is correct?
So FAA certificated mechanics or repairmen, they play a crucial role. They're the ones responsible for providing accurate weight and CG info after any maintenance or repair, any alteration to the aircraft.
Right, they're the ones on the ground making sure everything is good to go.
But ultimately, the buck stops with the pilot in command. That's the PIC.
The CIC, the one in the cockpit.
They are required to know the aircraft's weight, where that CG is located, the maximum allowable weight, and the approved CG limits before every single flight. They have to know this stuff cold.
So this data, it's not just a ballpark figure, right? It's very precise.
No, not at all. We're talking about a formal document here, the weight and balance report. It includes this very detailed equipment list showing the weights and what are called moment arms of all the equipment that makes up the aircraft's certificated empty weight.
Moment arms. Okay. I think for those of us who aren't pilots or mechanics, maybe we need to break down some of these terms. What exactly is the datum in this context, and how does it relate to these moment arms?
You got it. So the datum, Think of it as an imaginary vertical plane, or a line,
Yeah.
that the aircraft manufacturer establishes. It's the reference point for all longitudinal distances when we're talking weight and balance.
Okay, so it's like the 0 point on a ruler that runs the length of the aircraft.
You got it, exactly that. Now, a moment arm, that's the horizontal distance from this datum to the center of gravity of a particular item. It tells you how much leverage that weight has to cause a turning effect around the datum. It's kind of like a seesaw or a teeter-totter, where the distance from the center, that datum point, affects how much influence a weight has.
It's all about balance, right?
Yeah.
And this weight and balance report, this document sounds like it needs to be kept up to date.
Absolutely, it has to be current. And because things change over time, repairs, alterations, even just wear and tear, periodic weighing of the aircraft is really important, highly desirable.
The FAA recommends reweighing in several specific situations.
They do, yeah.
So we've talked about why this is important. Now, when exactly does an aircraft need to go back on the scales? When do we know it's time for a checkup?
Okay, well, the most obvious one is when it's originally certified.
Okay, so right from the start.
Yeah, right out of the gate. Think of it as setting that baseline. But then, anytime the aircraft goes through major alterations, anything that could affect its weight or where the CG is, a reweighing is necessary.
Makes sense. You add or subtract big components, you got to know the new numbers.
Exactly. And it's not just about the mechanics noticing changes. If a pilot reports that the aircraft just doesn't feel right in flight, feels consistently nose-heavy or tail-heavy, that's a big red flag,
Okay, yeah.
that the weight and balance might be off, and a reweighing should be considered. And finally, if there's any suspicion, any doubt at all, that the recorded weight and balance data might be inaccurate, it's always best to err on the side of caution and reweigh the aircraft.
So the pilots are really the first line of defense in noticing potential issues.
They are, yeah.
Since they're the ones flying it and feeling how it handles.
That's right.
Okay, so let's dive into the responsibility of certified mechanics when it comes to weight and balance. What are their duties after they've worked on an aircraft? What do they need to make sure of?
So their responsibilities are very clear-cut. First and foremost, after any repair or alteration, they have to calculate and ensure that the aircraft's weight and CG are still within the authorized limits, which are specified in the type certificate data sheet.
Right, the TCDS.
The TCDS and the aircraft's specifications. They can't just slap on a new part and call it a day. They have to think about how it affects the weight and balance.
They're doing the math, basically, to make sure everything is still safe to fly.
Exactly.
Right, yeah.
And second, they have to record the new empty weight center of gravity, or EWCG data. This goes in the aircraft's flight manual or its operating limitations.
Okay.
So the pilot always has the most up-to-date information. And finally, after any major work that could affect weight and balance, they have to provide the pilot with accurate information about the aircraft's current weight and where that EWCG is located.
So it's a chain of responsibility, starting with the mechanics providing the data, and then the pilots using that data to operate the aircraft safely. Okay, let's talk about the actual process of weighing an aircraft. What kind of equipment do we use for this? What are we talking about here?
So the handbook outlines two main types of scales. They're used for weighing aircraft: platform scales and load cell scales. Platform scales, you might also hear them called ramp wheel scales. They're generally low to the ground, easy to move around, and considered pretty safe and reliable.
Okay.
The aircraft is basically just rolled onto these pads with one scale under each wheel or skid. Now, these scales need to have a pretty hefty capacity, typically up to 60,000 pounds per scale, although most smaller aircraft won't come anywhere near that.
It's just amazing the scale of these things.
Yeah, it is.
So it seems like a straightforward process. Roll it on, get the readings. What about load cell scales? How are those different?
So load cell scales are another option. They're often less expensive initially, and they use these electronic load cells that are placed between jacks and jack pads on the aircraft's structure.
Okay.
So you actually have to jack the aircraft up for this method. The weight at each jacking point is then displayed on a control panel.
I see. So instead of weighing the wheels directly, you're weighing the points where the aircraft is lifted.
Exactly.
Okay, so there's a trade-off here, right?
Yeah, there is. Jacking an aircraft can be more of a hassle, and it does introduce a potential safety risk, which is why some operators prefer to avoid it.
Right.
Plus, the handbook points out that weighing with platform scales is usually much faster, about a third of the time compared to using load cells.
So convenience and speed are often in favor of platform scales. But if cost is a major concern, then load cells might be the way to go.
You got it.
Okay, so regardless of what type of scale you're using, Accuracy is obviously paramount, right?
Absolute critical.
Hmm.
Any scale used for aviation, whether it's manual or electronic, has to be protected from damage during storage and shipping, and they need to be checked for accuracy regularly.
Of course.
Usually the maximum time between calibration checks is 12 months,
Okay.
but it could be shorter depending on how often the scales are used and the local regulations.
Makes sense. It's like any measuring tool. You got to make sure it's still reading true.
Exactly. And ultimately, these scales should be sent back to the manufacturer for proper calibration and testing.
Right. You can't just keep using them forever without making sure they're still accurate.
Exactly.
Okay, so we've got the right equipment and it's all calibrated. What about preparing the aircraft itself for weighing? What needs to be done to make sure we're getting accurate readings?
Yeah, good point. You can't just roll it onto the scales as is.
Right, there's got to be some prep work.
There is, absolutely. Proper preparation is key for getting reliable weight and balance data. The first step is always to check the aircraft manufacturer's maintenance manual because they often have specific procedures for that particular model.
Okay, so always refer to the manual first.
Always. But there are also some general guidelines outlined in the handbook that apply across the board.
Let's start with the scales themselves. What needs to be done before we even bring the aircraft in?
So before you even think about rolling that aircraft in, you got to inspect the scales and set them to 0.
Okay.
This means adding and removing a known weight and making sure they consistently come back to 0.
You're basically making sure they're not biased in one direction or another.
Exactly. Do this a few times until you get a steady 0 reading. Also,
Okay.
make sure the scales are in the same environment where you'll be weighing the aircraft and give them at least 2 hours to adjust to the ambient temperature.
Oh, okay, so temperature plays a role.
It does, especially with electronic scales. Extreme temperatures, like below 40 degrees Fahrenheit or above 100 degrees Fahrenheit, should be avoided unless the scale is specifically designed for them, because temperature can affect the accuracy of the ratings.
Interesting. So temperature affects the scales. What about the aircraft itself? What kind of prep work needs to be done there?
So ideally, you want to weigh the aircraft inside a hangar to prevent any wind interference.
Okay, wind could definitely mess with the readings.
It could, yeah. It'll cause fluctuating measurements. The aircraft needs to be as clean as possible, inside and out. Pay special attention to the bilge area, make sure there's no trapped water or debris, and the exterior should be free of mud and dirt. And then double-check that all the required equipment is installed correctly according to the aircraft's equipment list.
Okay, so basically a squeaky, clean aircraft with all the right stuff in the right places.
You got it. And make sure there's no unlisted equipment on board.
Okay, so no extra stuff lying around.
Nope. If there is, the weight and balance records will need to be adjusted. Any permanent ballast has to be secured, and any temporary ballast needs to be removed.
So a clean, correctly configured aircraft on properly calibrated scales in a controlled environment. Got it. Now, what about fluids like fuel and oil? They can add a significant amount of weight, right?
You're absolutely right. Fuel and oil can make a big difference, and how they're handled during weighing is crucial. For fuel, always follow the manufacturer's instructions. If there are no specific instructions, the standard procedure is to drain the fuel until the gauges read empty when the aircraft is level.
Okay, so basically drain the tanks until they're showing empty.
Right. Any fuel that's left over is considered unusable fuel, and it's actually part of the aircraft's empty weight.
So even though it's unusable, you still have to account for it in the weight calculations.
Exactly. The amount of this residual fuel and its location, or ARM, are usually listed in the TCDS.
Got it. What if it's just not practical to drain all the fuel?
If draining isn't feasible, you can fill the tanks completely, weigh the aircraft, and then subtract the weight and moment of the full fuel load from the overall figures.
Okay, so you're basically working backwards.
Exactly.
Hmm.
And then you add back in the weight and moment of the residual fuel to get the correct empty weight. To figure out the weight of the fuel, you typically measure its specific gravity using a hydrometer and multiply that by the weight of pure water, which is about 8.345 pounds per gallon.
Specific gravity, so that's basically how dense the fuel is compared to water.
Exactly.
And that difference in density affects how much a given volume of fuel weighs.
You got it. It's worth noting that the temperature of the fuel can actually affect its weight per gallon, which can really add up when you're dealing with large fuel quantities.
So even a small difference in density because of temperature can have a noticeable impact.
It can, especially with larger aircraft. The handbook gives an example of how jet fuel weight can vary with temperature.
That's fascinating how even something like temperature can play a role in weight and balance. What about oil? How do we handle that during weighing?
Oil is interesting because how it's handled depends on when the aircraft was originally certified.
Okay.
So for older aircraft certified under CR Part 3, the engine oil isn't included in the empty weight.
Okay.
So you either have to drain it before weighing or subtract its weight from the readings. Any oil that can't be drained is considered part of the empty weight. Now, for newer aircraft, certified under 14 CFR Parts 23 and 25, full oil is included in the empty weight.
Okay, so different rules depending on when the aircraft was made.
Right. If you can't drain the oil in these newer aircraft, you fill the reservoir to the specified level, calculate its weight, which is usually around 7.5 pounds per gallon, and then subtract its weight and moment, making sure to add back the weight and arm of any undrainable oil, which you'll find in the TCDS.
So there's a specific procedure for each scenario.
Absolutely. Got to follow the rules. Now, what about other fluids in the aircraft?
Yeah, what about those? Are they included in the empty weight as well?
So any fluid needed for normal operation, like hydraulic fluid, should be at its full level when you're weighing. But things like potable water, water for the lavatory, and water for engine injection, those aren't part of the empty weight.
Okay, so those are considered separate.
Right.
Right.
And finally, before you weigh, always consult the aircraft service manual for the correct configuration of the aircraft, like the position of the landing gear and control surfaces. For helicopters, the main rotor needs to be in the right position as well.
Okay, so lots of preparation to make sure we get that baseline weight right.
It's all about the details.
Now, once the aircraft is on the scales, if we're using load cells, you mentioned jacking and leveling. What are the procedures and potential hazards there?
You're right, jacking does introduce some additional complexities. Ramp scales, as we talked about before, they eliminate the need for jacking entirely, which makes things a lot simpler. But if you do have to jack the aircraft up, you have to follow the manufacturer's recommendations to the letter.
Absolutely no cutting corners.
No cutting corners, safety first. Some aircraft might need special stress panels installed under the jack pads to spread the load. And when you're using wing jacks, always raise them simultaneously and make sure those safety collars are screwed down tight.
Right, so if one jack fails, the aircraft won't suddenly tilt or slip.
Exactly. You don't want any surprises when you're jacking an aircraft up in the air.
Definitely not. And leveling the aircraft is also crucial, right?
Absolutely essential.
Right.
When you're weighing an aircraft, it has to be in its level flight attitude.
Okay, so it's as if it's flying straight and level.
Exactly. That way, all the components are at their correct distances from the datum, which, as we discussed earlier, is that reference point for all longitudinal measurements.
Right, the 0 point on our imaginary ruler.
Precisely. The specific way to determine level flight attitude will be in the TCDS.
Okay.
Some aircraft use plumb lines, others have leveling lugs, or even use the upper door sill to place a spirit level. Helicopters often have built-in leveling indicators or plumb bobs to check both longitudinal and lateral level.
Interesting. So there are different methods, but the goal is the same level flight attitude.
Exactly. Now, when you're using load cells, leveling adjustments are usually made with the jacks themselves. If you're weighing from the wheels, you usually adjust the air pressure in the nose wheel shock strut to get it level.
It's all about precision.
It is, yeah.
Okay, so we've got the aircraft level, we've got the weight readings from each scale. How do we actually calculate the center of gravity? This is where those moment arms come into play, right?
Absolutely. So, first things first, you got to establish your datum.
Okay, back to our reference point.
Right. The handbook describes dropping a plumb line from the datum point and marking the floor. Then you draw a longitudinal line along the floor based on that mark. Next, you mark lateral lines where the main wheels are weighed, and a mark on the longitudinal line for the nose or tail wheel weighing point. These markings let you accurately measure those distances, those arms, for the datum to each weighing point.
So you're creating a physical map, basically, of where everything is relative to the datum.
Exactly. Once you have those arms and the net weight at each point, remember to subtract the tire weight of any chocks.
Right, we only want the weight of the aircraft itself.
You calculate the moment for each point,
Okay.
which is just the net weight multiplied by its arm. To find the overall CG, you add up all the individual moments to get the total moment, and you add up the net weights to get the total weight. Then you divide the total moment by the total weight, and that gives you the distance of the CG from the datum.
So CG equals total moment divided by total weight.
Bingo. That's the magic formula.
That's the one to remember. The handbook also mentions these EWCG formulas based on datum relationships. What are those all about?
So those formulas are basically shortcuts.
Okay, I like shortcuts.
Yeah, who doesn't? They let you calculate the CG based on the weights at the nose or tail wheel and the main wheels, along with the distance between them and the distance from the main wheels to the datum. The handbook lays out 4 different scenarios,
Okay.
depending on whether the datum is forward or aft of the main wheels and whether the aircraft has a nose wheel or a tail wheel.
Right, because those configurations would affect the calculations.
Exactly. Each scenario has its own specific formula that lets you calculate the CG relative to the datum using those key measurements.
Yeah, so you don't have to calculate each wheel individually if you know those overall weights and distances.
Exactly. It saves you a few steps.
Yeah.
For example, let's say the datum is forward of a nose wheel airplane.
Okay.
The formula involves subtracting a value based on the nose wheel weight and the distance between the wheels from the distance of the main wheels to the datum. If the datum is aft of the main wheels, you're adding or subtracting that value.
Got it.
And there are similar formulas for tailwheel aircraft. The main point here is that while the datum's location in these calculations changes, the actual physical location of the CG relative to the aircraft itself stays the same.
Right, the datum is just our reference point.
It is, yeah. It's like
Yeah.
measuring something with a ruler.
Hmm.
The length of the object doesn't change just because you're using a different starting point on the ruler.
That's a great analogy.
Yeah.
Okay, so the handbook also delves into this concept of the mean aerodynamic chord, or MAXC, especially for larger aircraft. How does that tie into the center of gravity, and why is the system used for larger aircraft?
Good question. So while we often talk about the CG in inches from the datum for smaller aircraft and helicopters, larger airplanes often express their CG location and range in relation to this mean aerodynamic chord, or MAC.
Okay, the MAC.
Now, the MAC is essentially the average width or chord of the wing.
So for a rectangular wing, it's pretty straightforward, right?
Yeah, for a rectangular wing, the chord is constant. But for tapered wings, which are common on larger aircraft because they're more aerodynamically efficient, the MAC represents the chord of an imaginary rectangular wing that would have the same aerodynamic characteristics as the actual tapered wing.
Okay, so it's a way to simplify the calculations for a more complex wing shape.
Exactly. Think of it as a representative chord line through the wing's aerodynamic center.
Got it. So why is this system preferred for larger aircraft?
It's preferred for larger, more complex aircraft because it gives you a consistent reference point on the wing itself,
Okay.
which is the primary lifting surface where those aerodynamic forces are acting. Expressing the CG as a percentage of the MAC makes it easier to understand how the loading affects the aircraft's stability and control characteristics, no matter the size of the aircraft or where the datum is located.
So it's a way to standardize the reference point for balance considerations, especially when you're dealing with different wing shapes and sizes.
Exactly, it provides that common ground.
No.
Now, when we're talking about the MAC, the manufacturer usually defines the location of its leading edge, the LEMAC, and its trailing edge, the TMAC, in inches from the datum.
Okay.
The CG location and its limits are then expressed as a percentage of the MAC, or %MAC.
So instead of saying the CG needs to be, say, 50 inches after the datum, you might say it needs to be at 25% of the MAC.
Precisely. Light aircraft often stick to inches from the datum, but for those big transport category aircraft, it's almost always %AC.
Okay.
And the reason for that is that the CG position relative to the wing's aerodynamic center of lift is super important for how the aircraft flies.
Right, it affects its stability and control.
Exactly. So by expressing both the CG location and the aerodynamic center in the same percentage terms, it simplifies the design and operational considerations.
It makes everything more consistent.
It does, yeah. Now, you can convert between CG in inches from the datum and %AC using some simple formula.
The handbook has an example, right?
It does, yeah.
Yeah.
It uses a hypothetical aircraft where the MC goes from station 144 inches, which is the LEMAC, to 206 inches, which is the TMAC. So that gives you a map length of 62 inches. And let's say the CG is at 161 inches from the datum.
Okay.
To get the %MAC, you first find the distance of the CG after the LEMAC, which is 17 inches in this case.
Oh.
Then you plug it into the formula. %MAC equals the distance after the LEMAC divided by the MC, all multiplied by 100. So that gives you 27.4% in this example.
Okay.
Now, if you know the %AC and want to find the CG in inches from the datum, you use a different formula.
Okay.
CG inches from datum equals the LEMAC plus the MC times the %AC divided by 100. In this case, it would be 161 inches.
So whether we're dealing with inches or percentages, it all comes down to knowing where that CG is and making sure it's where it needs to be.
Absolutely. It all boils down to that. And remember, weight distribution is just as important as the total weight.
Right. It's not just about being under the weight limit. It's about how that weight is distributed.
Exactly. And anytime you change the equipment on the aircraft, you need to update the equipment list and maintenance records. What was added, removed, relocated, the date, the mechanics information, all that needs to be documented.
So meticulous record keeping is essential.
It is,
Yeah.
yeah. Now, the CG, think of it as that imaginary balancing point where the nose-heavy and tail-heavy moments are equal.
Huh.
If you could suspend an aircraft from its CG, it would be perfectly balanced.
Like a seesaw.
Exactly. And as we discussed before, if you fly with the CG outside the approved limits, whether you're talking inches from the datum or percent at sea, you're compromising the aircraft's controllability and putting safety at risk. For instance, if the aircraft is too tail-heavy, it can become very susceptible to stalls, especially at low speeds, and recovery might be impossible.
So the takeaway here is that weight and balance is not something to be taken lightly.
Pun intended.
Okay, I see what you did there. But seriously, folks, this is crucial stuff.
It is.
We've really unpacked the ins and outs of aircraft weight and balance today, learner.
We have, yeah. We've talked about why it's so fundamental for safety and performance, how to accurately weigh an aircraft, and the methods for determining that all-important CG, whether it's measured from a datum or in relation to the AMR.
And hopefully you have a much clearer understanding now of what goes into making sure an aircraft is properly balanced. It's way more than just making sure you're not over the weight limit.
It is, yeah. It's a testament to the rigorous processes that ensure safe flight.
It really is. Understanding these principles gives you a whole new appreciation for how even small details can have huge consequences in complex systems like aircraft. It highlights the importance of precision and careful calculation, not just in aviation, but in engineering and transportation as a whole.
Absolutely.
So, for our final thought today, learner, think about how these principles of weight distribution and balance might apply to other things you encounter every day.
Yeah, think about it.
How about loading your car for a road trip or designing a stable building or bridge?
Good example.
What happens when the center of gravity shifts unexpectedly in those scenarios? Could there be unforeseen consequences? It's something to ponder. Thanks for joining us on this deep dive. Until next time, fly safe.